I think I've got this down. I'm trying to record my lectures like we would have done in class. I do miss seeing your beautiful faces, but for now, this is kind of what I'm doing. I hope it helps. Otherwise, if you have questions, you know you can always reach me. I am going to set up times for us to chat. I think we might do FaceTime a couple of times next week instead of just the one time today. So do keep that in mind. All right, so let's go through some chapter 17 stuff. We only covered sections 1 and 2, so we did not actually get very far through chapter 17 quite yet. The big thing that we will talk about today is the Henderson-Hasselbalch and just kind of how we can treat acid bases and what the common ion effect are. So those are like our 3 big topics today, okay? The first one's going to be the common ion effect, and this one is one that all of you actually demonstrated pretty well when I asked you questions this week. You were asked if you add something to a bromide solution, what would you do? And you all picked the one that had bromide, so it's very intuitive. And I do want to just go through this real quick to remind you, previous chapter, this was 2 chapters ago, chapter 15, we learned about Le Chatelier. Le Chatelier says that equilibrium would shift towards wherever the disturbance was. So this is saying if acetate ion, and acetate is of course this ion, whereas this is the acid of acetate, so acetic acid. If we added acetate ion to the solution, we are adding more stuff to this side of the balanced equation. So that means that all of it has to kind of start trying to shift back towards the left to get rid of what we've added. Okay. Then from there, we want to talk about how does this actually come into play with a common ion. So the ion effect, it has this really specific wording, and I will upload this lecture for you as I've done in the past. But it just kind of states that what we're talking about involves a strong electrolyte and an ion in common with a weak electrolyte. So if we add something, and let's look at this example of fluoride ion and an acid that are added together. And what we get is an equation that is represented by this acid dissociation constant Ka. We know that when this acid, HF, dissociates, it's going to dissociate into an F minus, so the conjugate base of HF, and the H3O plus, remember that's also H plus, the acid part of the ion. And that gets us this particular thing. And we know the Ka for this is this particular value. And so what we're asked is, how can we calculate the ion concentration of just fluoride in a solution that has both 0.2 molar HF and 0.1 molar HCl? So you may or may not recognize that this 0.1 molar of HCl has a common ion of H involved in this equation. If you can't spot it, remember that when HCl dissociates, it would dissociate into H plus and Cl minus. Obviously, the Cl has nothing to do with this equation, so it must be the H plus, which also is represented by H3O plus, don't forget. So what we're going to do is we're going to set up an ice table, and we've done this before, where we're going to go through and we're actually going to put our equation all the way out there. We know that, remember, liquids get ignored. We're going to put in what we were given initially, and then we're going to try and calculate a change and what happens at equilibrium. So for this, we're going to go ahead and we're going to do our x's. Remember that we are getting rid of the thing on the left at this point because we know we have 0 of something on the right. So we know this side is negative, and we know these are positives because the positive side has a 0 involved, right? So it would, if we put a negative x over here, would that even make sense? No, we can't subtract from 0. We're talking about finite quantities. Okay, so then we go through and we would we would get to our final equilibrium thing. And now one of the things you're going to notice is, what are they doing here? They're ignoring x. Look at that. You remember when we talked about that last chapter where we could ignore x in special situations. This is one of those special situations. And specifically, this is a special situation because of this particular K at equilibrium. So remember, if the K is really small, we can probably ignore x. Now, is that always the case? Probably not. Sorry, that's my husband. Send a man to the grocery store. So what is the next step now that we have an equilibrium thing and we have that K expression from the very beginning? It is, of course, to plug that information in to the expression to solve for x. Now, doing that gets us this particular value for this particular problem. Now, this x, remember, represents the change in what's happening up here. And our overall goal in this particular example was to calculate a pH. So what we're going to do is we're going to take that x, and we're going to subtract it from the initial concentration, or we're going to add it, to the initial concentration of the H plus. So now we know that the F minus concentration, which is definitely just going to be X at equilibrium, is going to be this 1.4 times 10 to the negative third. Now, we don't really care about that number. We care about what's happening to H3O plus. So we're going to take that 0.1 we started with. Remember, that comes from the HCl. It's the common ion, if you will. We're going to add the value of X we just got. We're going to see that that's really small and it really doesn't change this all that much. And we're going to get a pH when we plug it in of about 1. Okay, so the common ion effect will typically have an impact on whatever ion's concentration we're looking at, but in this particular case, it really didn't. We just took the pH of our HCl. Now, a couple of reasons this makes sense. HCl is a strong acid. A lot of the times it will have a huge effect on our acids and bases. I apologize if I'm talking really fast. It is about 11:15 and I'm meeting you guys at 11:30. I am going to upload this hopefully after we talk. This is the actual lecture thing. And I didn't realize I could do this on my computer until literally 15 minutes ago. So the next thing that we talk about are buffers. Now, buffers are just a really fancy method of keeping things within a range. So we use buffers if we want to resist pH changes, even if we're adding a strong acid. So say, like, the best example is going to be the human body. We don't want blood to change that much as far as pH is concerned, because if it does, it starts to degrade organs or tissues, or cells start to break apart. Those are all bad things that we don't want to happen in a person's body. And so blood is actually designed as a type of buffer. What it does is it resists changes to pH. Hold on, I'm going to figure out how to, I'm going to pause and come back. And I'm having to I'll try to piece these together. I don't really know how it's going to work. All right, so buffers are going to be solutions where we have a weak conjugate acid-base pair. It can be a weak conjugate acid with a base, or it can be a weak conjugate base with an acid. It doesn't actually matter which is which at this particular time. For what we're going to be looking at in terms of a buffer, understand that buffers are made with a acid conjugate base pair or base acid conjugate base, whatever pair. All right. So you have to have both the acid and the conjugate base, or the base and the conjugate acid, in order to make a successful buffer. So you have to have both things from both sides of any acid base equation. Now, that being said, what we're actually seeing is if we add something, then we're going to see that the addition of either a strong base, so OH minus, or strong acid does not significantly change the pH. It may decrease or increase, yes, but it does not significantly change. And what we see is no matter how we design this buffer, it should react that way with either strong acid or strong base. That is how buffers are created. Okay, so just to kind of give us a general idea of buffer calculations, we can put together an acid plus a base. Remember, water can be either, and we can get the conjugate acid, so H3O plus, and the conjugate base of that acid that you started with of the A minus. And then we can put that into a Ka. We've seen this before. Okay, this is not new. But what we're going to do next is we're actually going to look at what happens if we try to split this up and we take the negative log. What we're doing right now, what we're seeing right now, is the derivation of the Henderson-Hasselbalch equation. And so lots of magic, lots of math. You guys have seen the math before. The property of logs is something that we will talk about briefly today. But what that comes out to be is this particular equation. This is the Henderson-Hasselbalch equation. So pH equals pKa plus log of the base over the acid concentrations. These have to be concentrations. Now, remember what P means. It just means take the negative log of something. So pKa means negative log of the Ka. And I wish you guys could see me right now because I'm using my hands to describe things just like I always do when I talk, and you can't see them, so I don't know why I'm using my hands. So just an example of how to solve one of these, and I am going to go through this with you today a little bit, but just kind of, this is what I sent you via text message yesterday, and it was a description of the Henderson-Hasselbalch and how to use it. Now, some of you really grasped it really quick. Some of us, I think, kind of got a little confused on how to use it. The big thing with the Henderson-Hasselbalch is going to be identifying the base and the acid that go together. So for instance, in this particular example, we have lactic acid. So we're told this is the acid, this long thing. And then we're told sodium lactate. And you would need to recognize that lactate is the ion of the lactic acid. Just it's one of the polyatomics. It's one we didn't learn, but this is basically saying that this must be the conjugate base of this original acid. It also gives us the Ka for this equation. A lot of times you will have access to that particular thing. Sorry, I'm going to mute the computer because the computer doesn't know that I'm recording you for you. All right, so we have information. We have a Ka, we have a base concentration, we have an acid concentration. So we're going to go to the Henderson-Hasselbalch. Anytime you see the term buffer, Henderson-Hasselbalch should be the first thing you think because it's so simple. It works in so many situations, and if you can master this, you're going to be able to do those buffer problems no problem. So the first thing we're going to do is we're going to plug in the pKa. I know I have a Ka, so I'm going to take the negative log of that number, and I'm going to get a number. For this one, it was 3.85. And then I'm going to do the log of the base concentration over the acid. Remember, we just defined that. And I'm going to get some very small value. A lot of times this number comes out to be less than 1. pHs do not change by more than a unit of 1 underneath the rules of buffers in the Henderson-Hasselbalch equation. So the pH of this particular thing would have been 3.85, but it changed by about -8 units and went down to 3.77. So the buffer did exactly what it was meant to do. Now, we are going to talk a little bit further about pH ranges and how are bases and strong and acids related to buffers in general. But for now, really, that is what I want to stop at. Calculating pH changes in acids and in buffers, same way we just talked about. You're going to use the Henderson-Hasselbalch. Anytime you see the term Henderson-Hasselbalch or anytime you see the term buffer, think Henderson-Hasselbalch, just straight up out the wazoo. Try and figure out how can I use this particular thing that I know will work. In our particular case, here's an example of a pH change in a buffer that involves a 0.3 molar acetic acid and a 0.3 molar acetate solution. And a lot of times your conjugate bases are going to have some kind of an ion that you need to ignore, like sodium or lithium or whatever it might be. And then you make 1 liter of solution, which means you could get moles over liters, aka the molarity, which is what you need to plug in. So you're told what the pH of the buffer is. In this particular case, it wants you to calculate the pH of the solution after you've added more strong base. So in order to do this, we want to make sure that we've actually got everything written down. Here's our initial information. We're told what the pH is equal to. We're told that the pH will be equal to the pKa, and we know that the pKa of this particular reaction is this guy. That was taken from a table. Now, next thing we want to look at is the overall equation. So we put the acetate ion over here. We know that this is going to be in a base. Why did we know this? Because we were told we were adding the base. So we add this OH minus, and we get the conjugate base of the acetic acid on the left, and we get water because OH plus H makes H2O. So we know this is not going to take place in our equations at all, so we're going to basically ignore it. We're going to put in what we know about our initial concentrations. We were told we were starting with this, we were told we were starting with this, and we were told that we were going to be starting with this because we're going to add that. What we want to know is what happens in the after column. Now, in our particular case, we know that since OH is a strong base, that NaOH is a strong base, that every single one of these molecules is going to react with one of the H molecules. And since we know we have this molecule in excess, we also know that it's going to completely react. So we have to get rid of all of the OH until it's gone. And in doing that, it's going to be 1 to 1. So for every one of these goes away. So minus 0.020 moles will get us down to 0, and minus 0.020 moles on this side will get us down to 0.280. We know that when that happens, we're also going to then create the stuff on the right. So we know we're going to be creating 0.020 moles of this particular conjugate base. So now we know what our after reaction is. And the question was, what is the new pH? So we need to use the equilibrium concentrations of the base and the acid, the two you started with, in this equation. Now, this is actually supposed to say 0.28, so ignore that I just changed that. But this is the thing you're going to plug in. You know that this is the conjugate base because it's the thing that lost the H. And you know that this is the conjugate acid because it's the thing that we started with on the left side of the equation. Now, I'm sorry that these two are out of order. I'm not really sure why that is. I don't necessarily control the tables, but that's what happens. So when we do this math, we end up with this particular pH. So you can see adding a strong base did not change the pH very much. That is exactly what should happen when we're talking about our buffers, okay? And that is where we're going to stop for now. We talk about titrations next week. Titration math is pretty intense, and I know that it is intense. Plan on a few of these videos for sure, and then plan on FaceTime next week for sure. We'll do 11:30 to 12 at least twice next week just to kind of sit, chat, and talk about titrations in depth. Some of this stuff is kind of difficult. We are getting towards the easier stuff of the semester. Once we're through chapters 17 and I think it's 19, then we kind of do some random topics to wrap up the year. So look forward to that. I miss you all. All right, I'll see you in a bit.